Well, I really ought to start off by thanking all of you to come into this. And Radoslav, I am not an expert, so apologies there. And apologies to some of the rest of you who have seen some of this before, but you'll see part of the way through why I thought this was the right place to give this talk. Oh, I've got to do this, haven't I? Oh, I'm just holding it backwards. Thank you. Sorry, hold it the opposite way round from mine. Okay, so Radoslav's told you a bit about this. As I say, I'm not an expert. I got involved in this when the Royal Statistical Society set up a working party to look into a trial that went wrong. So we're talking about first-in-human trials, and what you do is you recruit healthy volunteers in cohorts. And you're proposing several doses of the drug, and for safety reasons you don't try higher doses before lower doses, and you always have placebo, partly because of the way humans react to the fact they're getting something. And in my experience, you should always assume cohort effects. For example, you might be trying out a drug on hay fever and there are pollens one week and not the next. So the question is, how should we design these trials? And one of my references at the end will be to the textbook that tells you how you're supposed to do it. So I'm going to call these, I've got this right, standard designs. Now you can see I'm a mathematician. I've got n doses. I just call them 1, 2, 3, 4 to n. I don't mean those are the real values. I mean that dose 2 is bigger than dose 1. And the point about a standard design is we have the same number of cohorts as we have doses. And I'm going to say m subjects per cohort. And we've heard the rules from Radoslav. In the first cohort, you can give placebo and dose 1. At cohort I, some subjects will get dose I, but nobody can get a higher dose. And so I've put in some notation for telling you how many subjects get dose I in cohort K, but I'm going to show you all the examples in a way that you needn't remember that notation. How am I going to assess the designs? Well, for the purposes of a short talk, I'm going to assume that cohort effects are fixed, but I have gone through it all with random effects as well. And I'm going for this A optimality, so this is what Radoslav did, minimize the average of the pairwise variances for all the pairwise comparisons of one dose with another or one dose with control. And you can think of other things you might do, but that's what I'm concentrating on in this talk. And the model I'm assuming, this is actually the same as Radoslav gave, except I'm too lazy to write down a general mean. I assume that my response is additive in a dose effect, a cohort effect, and the responses are uncorrelated, zero mean to the error common variance. I talk about the variance between dose I and dose J. Of course, what I mean is the variance of the estimate of the difference between their treatment effects. Now, if you show me your best design, I can cheat. I just double all the numbers of subjects. How do we stop me cheating? I do this thing which I call scaled variance. So if, and this really is an if because you're not allowed to do it, if you could have all the doses equally replicated in each cohort, then all the pairwise variances would look like that. So let's scale by that and say the scaled variance, Vij, so that's the variance we want to know divided by that thing. And if I only look at scaled variance, I can't cheat by simply increasing the number of people. So now let's look at the design. It's called the textbook design because it is the one in the medical textbook. And what do? You remember, and it's the placebo and dose K are all you put in cohort K. But everyone knows you should go for equal replication, so you aim for that. So that's the formula. What does it look like? Dose 1 comes in cohort 1, dose 2 in cohort 2, and so on. and you have that number the same all down the diagonal. Then you have placebo as well, much less of that, but in such a way that at the end of the day it adds up to the same replication as everything. That is the standard design given in textbooks. And you can calculate very easily the scaled variance between placebo and the rest, and it's half of the scaled variance between everything else. So when we started looking at this, Stephen Sen was chairing the RSS committee, and he said, well, actually, if we're given the constraint we can only have placebo and dose K in cohort K, why don't we go for the fact that we want to minimize those variances instead of going for the mantra of equal replication? And so what he said was, in each cohort, equally split between the new dose and the placebo. A simple idea. And you get these scaled variances there. You can calculate them. Now, I looked at these. I mean, I tried not to go on that RSS working party. I said, I don't know anything about clinical trials. I'm an agricultural statistician. Keep me off. And they said, yeah, but you know a bit about design of experiments. So, and I looked at this and I said, I wouldn't call those cohorts, I'd call them blocks. And I know something about block design. So thinking of the cohorts as blocks, suppose a cohort's got more than half of its subjects allocated to a single dose. That's not going to be good. You would never think about doing that in a block design, so why do you think of doing it just because we call them cohorts? So, I laid down a principle, we must never do that. In each cohort, no treatment should be given to more than half the subjects. Well, something else that you know about in block designs, you try to put as many different treatments as possible in each block. I mean, you can't do them all here because of these safety rules, but you can do better. And so, after sitting on this working party, I investigated various patterns. Now, I'm not like Radoslav or Wenke, I'm not a hot shot with algorithms. So what I do, I use GAP, which does exact computations, and I just investigate patterns. I think of a pattern, I look at it, and if that one seems better than that, then I put my brain back on and try and see what's what. And the reason I wanted to give this talk here at the Newton Institute was that some of this investigation happened when I was recovering from surgery. Now, my consultant said, yeah, no doctor would take time off, she would continue to do some work, you know, keep on with your research, that'll be good for you. I tried going into my office in the institution where I was working. They said, get out, you can't be here, you're on sick leave, so our insurance doesn't cover you working here. I came here, and David Wallace, who was at that time the director of the Newton Institute, said, welcome. Please come and sit in our library here and do whatever work you like. I sat there working quietly, you know, for as long as I didn't get tired, and I found the Newton staff incredibly supportive. And I got on with the work while I was here. And so what I came up with, after lots of slow work and slow thought, was my aim is to make those variances small. So what I'm going to do is each time I introduce a new dose, I'll put it on half the patients, but no more. And below that, it could be anything, but we can't have higher doses. And after quite a lot of investigation, I decided on the following. In the first cohort, equally split between placebo and dose 1. When we get to cohort K, put half the subjects on the new dose, and the remaining subjects, spread them out as equally as possible over the lower doses. And if you can't do it exactly, then you try to make the replication so far as equal as you can. So I'll give you an example of this uniform halving design. So n doses 4, so 4 cohorts, and we've got 8 people per cohort. The first cohort equally split between 0 and 1. In the second cohort, we have half on 4, then we split that equally. Third cohort, we have half on this dose there. We can't quite do it equally, so we give one more to dose 2, which hasn't had so much so far. The final cohort, we have half on the highest dose, and then those are all equal. Unfortunately, there isn't a nice mathematical formula for that anymore, even though I can give you the words for it, and you have to calculate the scaled variances numerically. But I can do that, and I can put them on a graph. Somebody was asking me 2 days ago how I draw my graphs. I'm afraid I'm very old-fashioned. I just use the basic LaTeX picture environment and plot them, and it works for me. Okay. So what I've got here, doses, and this is the average scaled pairwise variance. The open dots of that textbook design, look how they increase as the doses increase, and this is Stephen Sen's design. Doesn't increase anything like as badly. So let's home in on that, look at Stephen Sen's design, cut out the rest of it, and now we'll put in my design. Beats it by quite a lot. So I was quite pleased when I got to that. Okay. But then I had another thought, thinking from block designs. In your standard designs, you can't bring in the highest dose until the last cohort. So there's one treatment that occurs in only one block. Now, if you think about ordinary block designs, you estimate treatment differences well, if and only if you estimate block differences well, and you're never going to estimate differences between the last block and the others well if you're wasting all those resources on a treatment that never occurs anywhere else. So I thought, okay, let's try and get round that by saying we'll have one more cohort. And in that cohort, we can put any dose we like, and we can make sure that every dose occurs in at least 2 cohorts. So, what do I mean by an extended design? This slide looks very similar to what I had before, except that the number of cohorts is now one more than the number of doses. The rules are the same, apart from the last cohort, and the rule in the last cohort is you can put in anything you like. I didn't bother to try extending the textbook design because it's so bad. For Stephen Sen's design, I didn't try anything very complicated, but it did seem to me a fairly obvious thing was to say that before the last cohort, we've had the placebo taking up half of each cohort, very over-replicated compared to everything else. Let's just compensate for that by, in the last cohort, doing everything equally apart from placebo. And again, because that's a standard thing, no matter what the numbers are, you can calculate those numbers. It took me quite a long time faffing around to think what I should do for my uniform halving designs, and eventually I came in on this idea that about half the subjects in the final cohort should be given to say split equally across all treatments. And the rest you do for this thing of making replications as equal as possible. And again, if you need to, if you have inequalities, you favour the higher doses. So I'll show you how this works. This was the example I gave you before. How are we going to fill up the extra cohort? About half should be equally spread over all doses. So if I put 1, 1, 1, 1, 1, 5 is about half 8, and that's equally spread. Okay? Now what we've got to do is make up the overall replication. What's had the worst replication so far? Dose 4, so we give it 1. Now what's had the worst replication so far? Doses 3 and 4 are equally bad, give them both 1. Bing! That's it, we're full, so there you are. Can't give you a formula, but that's an algorithm a dog could work out. And there we've got the design. So those are the variances we had before. by extending the Stephen-Sen design, I get that. The variances come down quite a lot, and remember, by extending, I'm not cheating. These are scale variances, so relative to the number of people, the variances really do come down. What happens with the halving design? They do come down, but not as dramatically, and the only way I can feel good about that is saying that my design was good anyway, so it doesn't come down quite as well. So here's an example, just to try and show you. 2 designs for 4 doses, and I'm using 40 subjects. So over here I'm going to show you actual variances. So you'll see that I really am not cheating. This is a standard design in 4 cohorts. This is an extended design in 5 cohorts. This is the textbook one, so the 8's down there and the 2's there. This is the one that I've just shown you, and you all agreed with me, I saw you were nodding, that followed the rules. Now, what are the pairwise variances? Well, I've divided by sigma squared, and what do I mean? I mean this is the variance of the estimate of the difference between dose 1 and placebo. This one is, say, between dose 2 and dose 4. And with that standard textbook design, half the variances are 0.6 and half of them are 1.2. This is what they are in my design. 0.2, 0.3, 0.4. What are the averages? 1 1/3. And in my decades of work in agriculture, I had never reduced variance by a factor of 3. I used to say to my employers, if I reduce variance by 10% all the time, I'm worth employing. But a factor of 3? Wow. So, amongst the designs I looked at, the uniform halving designs are best. Amongst the standard designs, and also amongst the extended designs if you take the particular extension I gave. And both of them, the following rule just tells you what to do. In every cohort, half the subjects are distributed approximately equally amongst everything that's been used so far, and the remaining subjects are used to make up replication so far. So in particular, if you're bringing in a new dose, that's telling you half the subjects go on that dose, and the other half go on what we've had before. So I've shown you an example where the variance was reduced by a factor of 3. It was always a factor of at least 2 in the examples I looked at. As I say, the allocation rule, although there's not a formula, it's simple, doesn't depend on the numbers. A rather nice thing, if the trial has to be stopped early, then because you found a harmful dose, then actually fewer subjects would have been exposed to that dose than if you did the textbook design. And if you do stop the trial early, you've actually done the best design for the previous number of doses, and so if you wanted, you could then go on and do that extra cohort to do an extended design for that. There are similar results for random cohort effects, which I won't go into here, and something that Stephen-Sen always bangs on about is blinding. With these designs, blinding is much more effective, because in the textbook designs, you know you're either on placebo or dose whatever. So, I did that, it's published, and I want to try and say a little bit about more recent work. So, this is the notation I was using. Those are the doses, these are the cohorts, and these S numbers are the integers. This is the number of, say that there's a number of subjects who get dose 1 in cohort K. And there have to be zeros on the upper diagonal there, and the sum in each row is the number M of subjects per cohort. And as already been mentioned, Linda Haynes and Alan Clark have looked at this computationally for various values of N and M. For small values, they were able to do complete enumeration, and for larger values they did exchange algorithms. And they included A optimality and some other optimality criteria. So here's an example, and I think Radoslav gave this exact same example of what they came up with, because it's the size I'm looking at. 4 cohorts and 4 doses. And now you see down the diagonal, instead of going 4, 4, 4, 4, it's 4, and then it drops down to 3, a bit less than half. And so these numbers here aren't exactly equal, but they're not far off. So it's not quite the halving design, and it does beat it. And they found that by doing this thorough search. So a second strand of more recent work, I had an MSc student, and he got interested in this, and we decided to look at it with continuous designs. So instead of those S's being the number of people on that dose in that cohort, it's the proportion of that cohort that get that dose. And again, there have to be some zeros. Well, so he was called Brendan O'Neill, and he did this. But if you look at that table, you've got a lot of proportions to optimize over, and to cut down the search, because I say this was just a short MSc project, we said, okay, we'll work on what I call best so far. So when you're looking at cohort C, you use the best design you've already found for C-1 cohorts, and then just optimize the proportions in the final cohort. And so you get this with these fractions in there, and then once you've got the number of volunteers per cohort, you do m times the proportion. You can't just take them all to be the closest thing, because it might not make the right total, but you do the best you can. And in the examples we looked at, if there were different choices of ways of doing that, it made hardly any difference to the variance. So here's an example of one of the things that Brendan found for a best so far. I've put doses up to 4 and cohorts up to 5. So if we just had 2 doses, we would use that. 3, that. 4, that. And now that cohort doesn't have any more doses. So what we're doing there is actually, if we stop there, it's a standard design. If we go on, it's an extended design. So his method was to do a best so far, and then after each cohort, he worked out what would be the best way of having an extra cohort. And for example, if we've got 8 volunteers per cohort, then rounding this up, this looks very similar to both what I got and what Linda got. For example, 2 doses in 2 cohorts, 3 doses in 3 cohorts, 4 doses either in 4 cohorts or going on to a 5th cohort. So then Heiko Grossman and I thought, well, let's see if we can do something a bit more on optimizing those proportions. And so what Brendan had done this best so far to cut down the search. And Heiko and I have been able to show in some cases that so long as you definitely are allowed to have doses I and J in a cohort, then their relative proportions shouldn't change as you go on. And so we use that to cut down the search. And as I say, we can prove that that should be satisfied in some cases. And so just some very small examples. This is obviously the same as what Brendan got for 2 doses in 2 cohorts, or 2 doses going on into 3 cohorts. So you see that diagonal thing is a bit less than a half, and then those are equal. But if you know you're going to have 3 cohorts, you can make that a bit smaller, and so on. So that's work still in progress, unless we find out that Radoslav's completely beaten us out of it. So I did talk about this at a meeting nearly 3 years ago, the one you ran. And Vlad was there, and he said, Oh, well, I've got a suggestion, a better suggestion for what your optimality criterion should be. He said, we're talking about phase 1 trials. All we're trying to do here is really find the maximum tolerable dose. So what we're really interested in is comparing the one we stopped with the one before. So he said, go through all that again, but make your criterion minimizing that. Well, Val was there too, and he disagreed. He said what you ought to minimize is the variance for comparing that one with placebo, because that's the one regulators want to see. So there's an argument for both of those. And of course, because you don't know in advance where you might stop, if you're going to do this, you'd have to take a best so far approach. And just like in the one that I showed you, the results will be slightly different if you say in advance that whenever we stop, we'll put that extra cohort in. So again, just a couple of small examples, and I'm going to really cheat. If I stop at dose 2, then Vlad's and Val's criteria are the same, so I don't have to show you the different thing. Yeah, criteria. And it's similar to what we've seen before, but a bit different. That's a bit less than a half. Or if we know in advance, if we say that if we have to stop there, then we'll have a third cohort, then you can get away with a bit less there. But of course, as you go on for subsequent cohorts, the designs on those two criteria do become more and more different, because one tends to put more on the control and the others tend to put a lot on the last two doses. So that's it. Here are some references. As I say, there is a textbook which says you should do those designs I showed you at the start. This was our thing we did in the RSS report. Radoslav's already quoted that. That's Brendan's dissertation, and we've heard this paper of Linda that came out last year. So thank you for your attention.
I'd just say it's a shame that the dose finders don't like estimation, because that would be a really
I know they don't, but yeah. It's,
any questions?
Yeah, it's just I like your talk. It's a very interesting talk. Just a point is actually most of it is actually based on a subjective thing of like tolerability and adverse event profiling, and even in your design, dose is confined with cohort. So the investigator and the patient know if they're in cohort 3, that's when they're going to get the highest dose.
No, because not very many in cohort 3 get dose 3 compared to the standard one.
Yeah, but as you know it's confounded. And what people find is actually placebos by cohort, the adverse events increase.
Yeah,
and so people like to put, you might want to consider a restriction, which is a practical restriction, where you must have an allocation ratio of 2:1 or 3:1 of active to placebo. For that reason, they want to know at the end that there are still, I know it's like, it's for the adverse event monitoring, because the adverse events will be increasing with placebo as well.
Yeah. And
for that reason, they like to have an allocation ratio of 2:1 or 3:1.
But I think my designs do keep them in there.
It's still kept in there, but at the end you only had one person. The allocation ratio was more like 5:1. And the allocation ratio...
I kept them all in. So it's the question, is it just placebo or is it all of them? But yeah.
So within that cohort, they like to have allocation ratio of 2:1, which actually obviously removes some of the optimality.
That's right.
But for practical reasons, clinicians like to have to help them interpret in that cohort what the adverse events are.
I agree.
It could be a practical restriction
on what we do, which is very useful to know about. Yeah. Chris? Oh, sorry, you're in charge.
Oh, Chris.
It relates to both talks, and I think Radis have had examples that made it more of an interesting question. I was thinking in the formulation, which says you have to have at least one on dose K in cohort K, and so on, and that's a big driver to what you're allowed. But as you vary that, the monitoring of the safety before you progress to the next level can change an awful lot.
Yes, and that worries me a bit. Yeah.
And should that really not be part of the properties you're assessing, as well as estimating other things? How much are you protecting the patients?
I agree.
I think it's that relative. You had the one on the top dose more than.
Yes, I mean, and that's, so mine at least you never go below a half. But yeah,
Any kind of constraint.
yeah, exactly. That you could. Yeah, Radislav could
And
redo
each
it.
one
Yes.
could be an MSc student.
Yes. Thank you.
I think Wenke wants to tell you how to use
Yeah.
cuckoo.
No.
I thought you still raised your hand.
No, he knows I'm not clever enough for that.
No, just a comment. When you have a K treatments and one placebo, there's a standard result that says you should be allocating more subjects to the placebo in square root to K, where K is the number of treatments.
Yes.
Is that any help?
No, that's a standard result if you haven't got blocks. When you've got blocks, it doesn't. That's a sort of guideline, but it doesn't do everything. So yeah, I am aware of that. Yeah.
I was thinking that I think in this textbook they're cheating. Well, they don't only want to minimize the variance.
Of course.
They want to have enough patients exposed to the higher dose.
Yes.
They do PK and that. So in your designs, you have less patients in the higher dose.
Usually by the end, you have as many as you would have done before.
It's not what if you show your example, you know.
Well,
I understand that's better what you've done, and I thank you. But I think that I think you had the textbook design and your design. You know, when you say it's 1 and 0.3, do we have the same number of patients at the higher dose? I don't think so.
So,
Well, you see.
see for this one here, the textbook ends up with
Oh yes,
8.
versus
I end up with
7.
7.
Yes, okay,
It's
you're right.
it's not
Yes.
very far different.
No, it's not
yeah.
very. Okay.
That was something that I bore in mind. You do. So if it doesn't immediately seem to be unsafe,
Yeah.
you do want to go on and do enough people, expose enough people to it to get some information about it. Yeah.
Okay. Yeah.
Let's thank Professor Emerita.